I'm going to talk about asynchronous programming in Rust. And before we start, I just want to get the vibe of this room. So anyone who has written a web service or really any server before, please raise your hand. There are people that didn't write servers before, I guess. Who knows what async? Please raise your hand. Raise your hand. Who has written async in Rust before? Please raise your hand. It's a lot of people. I hope I can teach you something today. So before we start, I just want to say that I've never presented before. I've never stood in front of a crowd like this before, and I'm not really good at talking. So now that I've lowered everyone's expectation and kind of get some more self-confidence, I think we can start. So let's jump right into it. It's so.
Or just hold it close to your mouth.
Sure. So can everybody hear me?
Yeah.
Sure. So the async system is a tool that can help us build servers, web servers, microservices, and it can help us build servers that can handle billions of clients. So to start, and it's really annoying. To start this talk, I'm going to set some goals for ourselves. So by the end of this talk, everyone here is going to know the benefits of the async system. Everybody is going to have a mastery of the inner workings of the system. And we are going to do it by building an async runtime in Rust from zero. And if we have time, and we probably aren't going to have time, I'm also going to show some pitfalls so you can avoid them in your everyday use of the system. So to really start this conversation, we need to kind of define some kind of model, some target. And our target is going to be this echo server. So this is really a simple server. Any message we throw on it, it's just going to throw it back to the client. And our goal is to handle as many clients as possible. So let's discuss the different ways we can start to implement this server. So we are going to start by talking about blocking.io and implement it using blocking.io. We are then going to realize that blocking.io is not the most efficient way. So we are going to try non-blocking.io. We are going to realize that non-blocking.io doesn't make sense without something like an event poll, and we have some other alternatives. And at the end, we are going to welcome the async system into our life. So this is how we can implement the main function of this echo server using blocking.io. And the idea in blocking.io is that every call to an IO bound request, like the accept method on this listener, is going to block our entire thread until we have some connection on it, until the event is ready. And what it means is that pretty much for any other IO request we are going to create, we are going to need to allocate a thread. And blocking.io, while it's like really easy to use and extremely easy to reason about, using it means we lose control over our thread. Losing control over our thread means that we need to allocate another OS thread for almost any other IO request we make. Any OS thread we create is going to pre-allocate a lot of resources. And if it's not enough, just moving between these threads requires context switches, which is expensive. Maybe we can do better. So we try a different approach. We try non-blocking.io. And in non-blocking.io, the operating system is going to tell us, hey, buddy, you don't want me to block anymore? Fine. I'm not going to block you anymore. Now you will need to figure out something. And we don't really have something to figure out. So we fall into this busy waiting hell. And what happens now is that when we call accept on the listener, we have like one of three options. We either have like a result that can be a connection and everybody is happy, or we have like an actual error and it doesn't really matter, we can just panic. We are still in the happy phase of this. But we also have the situation where the operating system tells us, hey buddy, I want to block, but you don't want me to block. And what we need to do in this situation is basically nothing. We can just keep begging the operating system, hey, maybe now you have a new connection. Hey, maybe now you have a new connection. Maybe now. No, we really don't want to do it. We are just going to waste our CPU time for really no purpose. This is not better from blocking.io. So while blocking all the time isn't that efficient, we realized that blocking is still kind of important, and we do want to block, but only when we have no work to do. And different operating systems offer like different solutions to this problem, and the solution I've decided today is one of the solutions in the Linux operating system. It's called event poll. And it's not even the only solution that Linux provides us. And just to briefly explain it, because we are going to use it directly and see it in more details later, the idea with event poll is that we are going to register like a list of events to the operating system and tell it, hey, here is all the things I care about. I don't have anything better to do. Wake me up when any of the events is ready and tell me exactly which event is ready, so I don't need to just spam you on each of the events to figure it out myself. And so the problem with event pool is that it's too low level. I don't want to write this code, to be fair. It looks like a mess. It's hard to reason about, and it's prone to errors like deadlocks and data collisions and many others. So I would much rather use the so-called less efficient blocking I/O and just pay for more hardware. I guess it's free nowadays, either way. So, and like, what about my Windows system? Event poll is only relevant to Linux. So what we have now is like a low-level problem, and to deal with low-level problems, we usually use high-level languages. And the solution that many programming languages provide is called user space threads, or more conventionally, tasks. And introducing something like tasks into a programming language includes a lot of our design choices, and really none of them make a clear answer. It's just trade-offs that you need to pay. And these trade-offs are going to shape almost any program that will be written in the language in the far future. So before we talk about the interesting part, like what do we have in Rust, I still want you to taste at least some of the more important questions. So the first thing we need to talk about as language designers is what does the user, and when I say user, I mean us, the programmers that are going to use the language, what do we actually need control as users? Do we even need to know about the existence of tasks? Maybe we can provide the user with an API that looks like blocking I/O, but it actually uses tasks behind the scene, and everything is like in user space, and everyone is happy. Or maybe we don't want to hide it from the user, and we don't even want to provide the user with a runtime. We just want to provide it with the infrastructure to build one. And also, what happens about the stack? When we use OS threads, the OS is going to pre-allocate us like a big stack that will probably be enough. But we kind of want to avoid threads just to not get this big stack that the OS is going to allocate for us. So what are we going to do? And what do we have in Rust? So in Rust, we choose cooperative scheduling, and it's not really we choose, it was chosen for us. Rust doesn't provide us a runtime at all. It just provides some kind of infrastructure around that can help us build a runtime ourselves and help us interact with this runtime. And more concretely, it provides us with this weird future trait that we are really going to get into it in just a moment. And along this future trait, it's going to provide us with this really, really strong syntax sugar that makes writing async code almost indifferent from writing normal Rust code. And jumping into, or let's try in this attempt to implement the echo server, we are going to try the async system to solve this problem. So this is how the main function can look like using the async system in Rust. And this code is combined with the runtime we are going to write today together. This is actually code that is going to run by the end of this presentation if we will reach it. And we will even run it together and see it actually works. So just from a quick look at this, I think that it's not that different from blocking I/O. We have this async fn, which is a syntax sugar. We have this await, which is another syntax sugar. We have this scheduler spawn that I think everyone can at this point guess is just a thread spawn, but for tasks and not threads. So it's really good. This is exactly what we wanted. So now let's talk about futures, the fun. So tasks are great, but the scope tasks cover is a bit too big. And in Rust, we want to talk about something smaller, and the game is going to be about futures. So to understand futures, let's try to break them down step by step. So this is the future trait. Anything that implements this trait becomes a future in our system. And this trait is like, I think, really, really simple. It has only this poll function. And to understand this poll function, let's look at the return type. So whenever we call this poll function, we expect it to do one of two. It's either going to return us ready, which means that the future is done. We have a result. We don't care about it anymore. The computation is completed. Or it's going to return us this pending. And when it returns suspending, the future is going to somehow register something, and we are going to see how it's going to do it. But it's going to register something behind the scenes, so it can tell the runtime in the future when it wants to be scheduled again. So we aren't going to schedule it from the runtime. The runtime isn't going to schedule it for no reason anymore. So now we can de-sugar a bit the async main function we had before, and see that async function is really just a normal function that returns this impl future, or just a future. And the actual output of an async function is going to be the output of the future. And what it means for us is that to actually get the output of a async function, we are going to either await it from another async function like here, or we are going to spawn it on the runtime. So what is spawning again? So not all futures are equal. The boss in this game is the future that is spawned on a runtime and becomes a task. And I hope you remember what is task. So below the task, we have something that looks like a tree. And this tree contains all the futures that our task is going to rely on, directly or indirectly. And I would like to split them into like 3 types. So the first type of futures are what I would like to call the normal futures. And these are the types we are, as the users of the language, are going to write. Like the async main function we have seen before, this is one of these normal futures. These futures are mostly going to be written using the async await syntax sugar. The second type are what I would like to call dumb futures. And I call them dumb not because they don't do anything useful, because they don't interact directly with the runtime. And this means that they probably aren't going to handle I/O. They are not interesting for this talk. The last, and I would like to say the most important type of futures, are the leaf futures. Leaf futures are futures that interact directly with the runtime, and they need to be provided by the runtime. We cannot write them as a user. The runtime isn't going to be useful without them. And this future usually like directly handle I/O requests, like accepting new connection on a listener, like we have seen before. And the way they are going to do it is by registering themselves to the reactor. So if you remember when I've said the future is going to do something behind the scene, the reactor is like what it's going to use. It's going to register itself to the reactor, and we still don't really know what the reactor, but the reactor is like a kind of subsystem in our runtime that is going to manage the event pool. So this is how we break this down into steps inside the runtime, and we are going to see it. And whenever the reactor receives an event that's relevant to the future that registers it, it's the one that is going to tell the runtime, hey, you need to run this future. And we are really going to dive more and more into it. So no worries if you don't get it in full right now. So now that we understand why we want async and have some basic understanding of what is a future, I at least hope everyone understands, I think it's time to write a runtime ourselves. And I think this is a good point for questions. So if anyone has a question until this point.
Slide 19, you showed that the future Eylon, has ready and pending. But what happens when we get an exception?
We get an exception.
So it is part of the ready response?
So we don't have exceptions in Rust. We have like a result. You mean if we have a result. So result is just part of the type you can return in ready. If you have an error, your future isn't pending. It's done. It's just done with an error. Any other questions? I mean, it's fine. I can just say the questions again if it's needed for there. Well, then I think we can just go on. I mean, the problem is also I hear my own voice and I don't know.
Don't worry, they're a little more quiet behind us.
Yeah. So this is a rough model of the runtime we are going to build. And it doesn't really look big, and it's a really simple runtime. The runtime is going to be single-threaded and built from two main subsystems. The first is the scheduler, and the scheduler is going to operate on the scope of tasks, not futures, and it's just going to run in a loop and execute any pending tasks we have, and we will understand what we mean by pending tasks. And whenever there are still tasks in the system, so the runtime still needs to run, but no active tasks. So all the tasks in the system just wait on events that are blocking it. It's going to pass the CPU time to the reactor. And the reactor is the second main subsystem we have in the runtime. And the reactor is the one in charge of the event pool. And whenever the reactor is given the runtime, given the CPU time from the scheduler, it's going to block on the event pool, which is exactly what we wanted at the start. And whenever it's woken up by the operating system, it's going to go through the list of events that were registered on it and just wake up the correct futures that registered themselves to the reactor. And it's going to do it using this waker. So the reactor doesn't actually know of the existence of the scheduler. It's just as a list of futures and list of wakers. And whenever it calls wake on waker, the waker knows to go to the scheduler, tell it, hey, please schedule this task ID. And we are really going to write it ourselves, so we really understand it by the end. So I think we can, if there is really no questions, I think we can jump right into it and start writing our scheduler. So the scheduler is a simple struct, and to make it work, and to make the workway tasks really simple, I've decided that we are going to use this hash map, and this hash map is like kind of a local area allocator, and the idea is that these task IDs, and we still didn't define task IDs, so we don't know what they are, but the idea is that these task IDs are going to act like local pointers, and these local pointers are going to be local to the scheduler. And it also contains this pending list where we just drop these task IDs, and because they are now like local pointers, we can just throw them around. They are just numbers. And otherwise, to make the work even more simple, because the scheduler is going to be used at many parts of the runtime, I just put it on the thread local and forget about it. So now we need to fill the types, the task ID and the task. So task ID is just a new type pattern over usize. Again, it's just a pointer, just a local pointer. And task is going to be pin box future. And we don't really going to talk about pin in this talk. So if anyone is interested, you can come to me at the end. I will be happy to explain in like 30 minutes, in about 30 minutes what pin means. But other than this, like I decided to make the runtime extremely simple and make futures not return any output. And it doesn't mean that futures in our runtime can't return output. It's just futures that are spawned on the runtime. So tasks can't return output. This is just to make things simple. So next, we are going to implement the scheduler. And we start with an internal function, schedule. And schedule is really simple. It's only going to be used by a waker. And whenever it's provided with this local pointer, a task ID, it just put it into the pending list. Simple. The next function we are going to implement is spawn. And it's important to note that spawn is part of our public interface. Spawn is one of the two functions we are going to provide the user. And to quickly iterate through the function, we start by boxing our future. So we allocate it on the heap. We then borrow the scheduler, insert it into our local allocator, and schedule it. And it's really, really important that we schedule it at the end. Because remember, if we don't call the poll function the first time and provide it with context, and we will see what context means, so we don't provide it with the means to wake itself later on, the game isn't going to start. It's not going to do anything interesting. The next function we are going to implement is block-on, which is also part of the public interface. And block-on is the function that is going to start the executor, and it does it by spawning the main task. And main task isn't really any special. It's just the first future we are going to spawn on the runtime because we need some future to start this conversation. And main task can later on like spawn new futures that will become tasks on a runtime. Otherwise, it does some housekeeping, like injecting the scheduler into our local thread, remove it when we are done, and start the runtime. So let's jump into the interesting part. Let's start the runtime. So the first part in the loop, if you remember, I've said it, the scheduler is just going to run in a loop. The first part in the loop uses some really interesting pattern in Rust, so I just want to iterate it quickly for people that may not know it. The scheduler has inside it a list of pending queue, and we want to iterate through this queue, while we also want to be able to push new pending task IDs into this pending queue. So what we are going to do is basically steal the queue from the scheduler, and We do it using this std memtake. And what it's going to do is leave a new empty queue on the scheduler that can later on be filled. The second part of the loop is simply iterating over the pending tasks and executing them. And this is like the function that is going to call pull. We are going to see how it's done later. And the last part is to check the status of the runtime. If there is still work to do, we go to another run through this loop. We still have tasks to execute. If there are no tasks left in the system, then we can just return. Otherwise, there are no pending tasks. All the tasks are blocked on kind of IO events of these IO-bound requests, and we don't really have any reactor yet. We know that we need a reactor to block here, but we don't have a reactor, so we leave it to do for now. So we start by implementing this helper function, this exec status, and this simply checks if there are no tasks. There are no tasks, no pending, there are no pending, otherwise we have work to do. Just wanted to fill it to have completeness. The second function, the helper, and the more interesting one is the one that is going to actually poll on the task which is going to like execute it. And in the first step, we check if the task ID, this local pointer, even exists. If the local pointer doesn't exist, we can just return. We are done. We don't have anything to do. But if the local pointer actually exists, we want to remove the task from the scheduler. And the reason we want to remove the task from the scheduler is because we don't want to borrow the scheduler while we also execute this task which is going to borrow this task. Otherwise, the task wouldn't be able to spawn new tasks on the scheduler. The second part of this function, we are going to create a waker from ID, from this local pointer, and we don't really care about how waker work at this point. All we care about is that we can turn a task ID into a waker, and whenever we call wake on this waker, it's going to call the scheduler on the schedule and schedule our task. Otherwise, we just call poll directly on the task, provide it with its waker, and then it's going to return us one of two. Either pending, and if it returns pending, it means it still has work to do, so we need to put it back into the scheduler. And if it returns us ready, it means it's done. And if the task is done, because we simplified the runtime and we don't have return types for tasks, we can just drop it. It's done. It doesn't have anything interesting left in the system. So we are finally done with the scheduler. We can mark it off and move on to the reactor. So as promised, the reactor simply manages epoll and also manages like this hash map of wakers. And just to explain briefly, epoll is part of the Nix crate, and the Nix crate just provides us like high-level Rust bindings to libc, like safe Rust bindings to libc, so we don't need to handle any unsafe code here, and I really don't want to write unsafe. And like with the scheduler, to make the reactor extremely easy, we are also injecting it into our local thread. So before we start to implement the reactor, I want to talk about the lifetime of a leaf future. Because remember, a reactor is really there for the leaf future. So a leaf future starts by registering itself in the reactor. Then whenever it is pulled, and the event is still not ready, like the future is not done yet, it needs to update the reactor with a new version of the waker. And we are going to talk about why we need the newest version of the waker. But whenever, and the last part of the lifetime isn't when the event done actually, it's when it's dropped. And why it's really important that whenever the leaf future is dropped, it doesn't matter if the event is ready or not, we remove the leaf future from the reactor because the future doesn't exist to be executed anymore. So now that we better understand what the leaf future needs, we can start implementing the reactor. And the first function we are going to provide is the register. And it's important to notice that while this function is public function, the reactor itself isn't. It's just kind of internal interface for the leaf futures we will write later. And there is also this file descriptor. And I didn't intend to talk about file descriptors, but I was told that it's better to at least drop a word about it. So in Linux, everything is a file. And we are now using event poll, so we are in the Linux world. So if we have a socket, we can write to a socket, we can read from a socket. A socket is just a file. And to identify open files in our process, we use this thing called file descriptor. So file descriptor is like a task ID, this local pointer. And we also do this really dirty trick. So because file descriptor is just a number, we can just cast it to a number and use it as an internal ID for our system. Again, this is just to make things simple. And otherwise, we also add it to the epoll. we register it using the file descriptor that identifies the event, and we also provided the ID. And it's important that we provide it with ID because when the EPOL provide us with a list of events after we blocked on it, and we are going to see it, it's going to tell us which IDs of events are relevant for us. The next function we will implement is update waker, and this function doesn't do anything special. It simply stores the newest version of the waker, and we still don't really understand why. The next function is remove. Again, it just maps the lifetime of a leaf future, and it simply deletes it. It deletes it from the EPOL and remembers to remove the waker because it's not relevant anymore. And the last part isn't really directly correlated to the leaf futures, and this is the block function. This is the function that we needed for the scheduler. And the block function is going to start by just blocking on the EPOL, and we kind of understand why now. And whenever it's woken up, whenever the operating system provides it with list of events that are now ready, it's going to go through this event. It's then going to take the data from them, and this is like the ID we provided the event back when we registered the event. And this ID is really just like a file descriptor, like we did a dirty trick. And then we can check the hash map to check if the waker exists. And if it exists, we call wake by ref. And if you remember, when we call wake on waker, it's going to tell the scheduler, hey, please schedule this task ID. It's just like an ID, like a masked ID. So we are finally done with the reactor and maybe with the runtime, but not really. We're actually not done with the scheduler. We still need to fill some parts. So the first part is just to remember to do this housekeeping, injecting the reactor into the local thread. And the second part is to actually block on the reactor. Remember, we left that to do back then. And the runtime is kind of done. I mean, almost done. If we go back to our mental model of a future, of a task, we remember that this leaf future thing. And I think we talk about it enough that everyone remembers it. And for our runtime to actually be interesting and useful, we still need to provide leaf futures. So before we start mirroring STDs, does anyone have questions? No questions. So providing leaf futures is really about mirroring STD. And the idea by mirroring STD is that every blocking function, so back then we have this accept function, and the accept is going to block our thread. We are going to replace this accept function with a function that returns a future. And now we can await this future or spawn it or something. So since our goal at the end of this talk is have a running echo server that actually works, what we are going to implement now, what we are going to mirror from STD, is just like the net module or even a small subset from the net module. So we start by mirroring STD's TCP listener, and we do it by simply wrapping around it. We then start by implementing its bind method, and we directly forward this call down to the listener that we wrapped around, but we also remember to make it non-blocking, because we still want to be in the world of non-blocking I/O. We then continue to the accept method, which was like the source of all problem at the start. And now this method doesn't return like directly a result, it returns a future. And the result type, the output of this future, looks really similar to the output of accept, but this TCP stream is another wrapper, it's another part of the STD we mirror. It's not an actually TCP stream of STD. So now let's write the actual future that is going to be returned from accept. And well, this as well just wrap around TCP listener, so it's not too much interesting. And before we continue and start implementing it, I just want to iterate again the lifetime of the leaf future. So it starts by registering itself, it then updates the reactor, it then removes itself. So we start by writing the new function, and at the new function we register the leaf futures. And now we can see how it's done from the leaf part and not the reactor part. We then start by implementing this future on the leaf future, and this is the first time we see an implementation of future by end. And to implement this, we are just going to direct the call directly to accept. And again, as we remember it, like when we just started, we had these three options. The first option is when we get pull ready, and the first option is when we actually get a connection, and whenever we get a connection, we can just return ready, we are done. But we do remember to wrap it with TCP stream, because again, the TCP stream we need to return is a mirrored part of STD. Why does it not continue? So the second part is whenever the operating system tells us, hey buddy, I really, really want to block here. And before we didn't add anything smart to do, but now we have something really, really smart to do. And it's to just register it on the reactor. And now why do we want to update the waker every single time? So while the runtime isn't really going to call poll after we return pending, or it's not going to call it for no reason at least, it still may call it, and still entirely possible in a really, really big system that this function poll will be called like thousands times. And this means that putting except here isn't the most efficient solution, but again, it's just simple. But it also means that the waker we are provided each time can change and can point to different tasks. And the event may still not be ready. So we always need to tell the reactor what is the latest version of the waker. So when it call wake on a waker, it actually wake us. The last part is when we get pull ready. And it's when we get error. And error is just a result. Again, someone asked before. We can just done. The future is done. We can just return this error. And the last part in the lifetime in the lifetime of a leaf future is whenever we are dropped. And again, it doesn't matter if the event is ready or not. Whenever we are dropped, we need to remove ourselves from the reactor. The waker has no meaning anymore. And the next part is to map TCP stream. And I really don't want to write any more boilerplate, so we are kind of done. This is time for a live demo. The echo server actually works. So, by the way, are there any questions? No questions. Explanation is really good, I guess. So this is the runtime. We have the crate RT Tokyo, wait, Y, and this is like the runtime. Yeah, it's not Tokyo, the popular crate that we are going to talk about. But we have like the runtime. You can see here is the reactor. We have the scheduler. I can't really use it like this. And we also have this TCP, which is like the net module that we mirrored. And I've also wrote like the rest of the functions we need for an echo server. And more importantly, we have this great echo server, and echo server is like the actual server, the echo server we wanted to implement. And now we can see that the main function, the actual main function of the echo server, is just going to create the scheduler and then block on the async main. The async main, I think we've seen enough times that I don't need to talk about it. But we haven't seen this connection handler. And this connection handler is another async function. It's one of the normal features in our lifetime. And all it really does is just read from the stream. Whatever it reads from the stream, it writes directly back to the stream. And if we get an EOF, we can just return. We are done. So this is really annoying, by the way. I can't see like the screen on my laptop, which is really annoying. So we can run it. And then we can open a new console and close this thing. And we can do like, I think this will work. And we can do netcut to connect to it. And I can't even see it, so I don't know why it's stuck. But yeah, but I can't see the screen, so I need to do it. This is really annoying. It works, I promise. So let's just go to the next terminal. Yeah, maybe this will work. Yeah, and now whatever we write is output. Oh, nice. Okay? So whatever we write is directly outputted to the terminal. And we can see that we can create like another connection, and whatever we write is also outputted, so it is concurrent. We achieved what we wanted, and all we used is just a single thread. So I guess we can just, if there are still no questions, we can jump right back to the presentation and recap things. So okay, it's this.
This is all running on a single thread.
Everything runs on a single thread. Have you seen us spawn any thread? other than single. Everything is just in this main loop of the scheduler.
Okay.
Then the scheduler just schedule tasks by one. And it's really important to remember that if one of the tasks is like a bad child and it decides to just eat the entire CPU and never yield, then we are stuck. The idea of this is why we call it cooperative scheduling. If you don't yield, there isn't a game to talk about.
Got it.
So just to recap, we started with blocking I/O and realized that blocking I/O may not be the most efficient way. So we decided to try non-blocking I/O and realized that to make sense of non-blocking I/O, we need something like event poll. Event poll is way too low level for my liking at least. So we wanted some language level solution. In Rust, the solution we have is the async system. And in the async system, we don't really talk about tasks, which are these user space threads. We talk about futures. And a task is just a future that was spawned on the runtime. And just to finish it, just some last words. Please don't write a runtime yourself. I don't recommend it. I mean, it's great if you write a runtime to learn. It's great if you have a really good reason and deep understanding. But unless you have a really, really good reason and you're going to use it for production, please use something like Tokyo. So Tokyo, and this time with I, is like the most popular runtime, I think. It's extremely flexible. It's already made for production, so you can just throw it at your work and like trust it to work. And it will cover probably any generic need you have from an I/O-based application. I've seen people use it successfully in embedded and other types of system. And in embedded, it can even replace a real-time operating system, so it can actually be a scheduler. And then you kind of want to think about like tasks that are going to block and eat all the CPU, so you want to like inject yields in them, so they give time for the other tasks to run on the system. And yeah, but the thing with the common pitfalls is that this is still before we dropped some material, so it doesn't contain the part you wanted to hear. Sorry. So just a small point I want to at least say this. So if you remember, this is like how the task looks like, and it basically contains like an entire tree below it, and every future inside this tree is also contained in an entire tree below it, and basically the tasks. Like, remember when I said, what do we have to do with stacks? So basically, our task is going to contain this entire tree, or in other words, it's stack. So basically, when we allocate the tasks, and we are doing it right now using box, we basically pre-allocate the biggest stack it will ever need, or what I personally like to call like a perfect size stack. And it means that we may allocate bigger stacks than we actually need. So just briefly, here is like, let's say we have a big future, and this is like really, really big, like let's say 10 gigabytes of memory, and you're doing something wrong if your future is this big. And we start iterating through the future, and we realize that somewhere down this tree, we have this big future, and you are the source of all problems. And we also don't rely on you more than like 0.1% of the time. Like it's somewhere inside an if, but just because we are weighted somewhere in our lifetime, we still need to allocate it. So we can instead not allocate it. We can try to point to it. We can allocate this task, this future inside the pin box, and maybe we'll have time to actually talk about pin. And instead what we hold inside our tasks, inside our big tree future is just a pointer. And now we don't even need to allocate it. It's like segmented task. We only allocate it whenever we actually need to use it, but we are paying with double allocations. And just to recap a few bits about like async FN. So our async functions are actually just functions that return a future. The compiler needs to generate the future from the function body. And if we hold data across data waypoints, we actually need this data to live inside our future. So it means that the future is going to be bigger, fatter if you want. And we can cut the futures. We can cut our tree using this box pin. And in general, I would recommend to aim to keep your futures as small as possible. And the reason for this is actually this funny line. The syntax sugar that the async await provides us is great, but it's actually not free. We will really like it to be free, but it's actually full of bugs. And there is this example here, and maybe I can open it for everyone to see. So maybe it will open. So here is just one example. And this is an example of how the sizes of futures does just double every time. So you can get like from few megabyte to a couple of gigabyte in just creating a big tree for no reason. And it's just a good rule of thumb to make your futures as small as possible. So now again, I want to ask, where is my food? I'm really hungry. And
It's coming, don't worry.
yeah, and I mean, this is basically all I've prepared for this talk. Now, there was more material, so if anyone is interested on Pin and we have the time, I can try to talk about it. What do you say?
I thought you were going to talk about some anti-patterns of things to do and not to do with async.
I mean, they are not ready because we thought we aren't going to have
Okay,
time.
that's fine.
I mean, this is a good anti-pattern, by the way. Keep your futures as small as possible. It's really important. The anti-pattern is here. I know what's your anti-pattern already.
Oh, you mean,
It's like not catching the lifetime.
yes.
So it's in here. It's just not prepared, so I'm not going to be able. So it's this one, right?
Yeah.
Yeah, but it's not really prepared for the whole. So, I mean, do we have extra time?
Yes, we do.
So I can iterate it really quickly. So I think it's there. So let's say you have an async function, and the async function captures some data. And it really only uses this data before the first call to .await. So what happens right now is that because it captures data before this call to .await, it's going to need to capture this reference. It's going to need to capture the lifetime of the sum data. And if we try to rewrite it a bit, it actually looks like this. So we actually can see this lifetime. So now the futures return needs to capture the lifetime of some data. But some data isn't actually all between .await points. And it may be that we need some data to actually be executed next to the call to some future. But if we don't need it, we can just, now that it's written this way, we can just rewrite it this way. We can move the use of some data outside the async block. And now the future return doesn't need to rely on it anymore. Matt really doesn't want me to talk about this one, so maybe I won't.
We actually have a question in the back. Hold on a second.
Can you give him the microphone?
I have a question. I see you have a pin method, the pin truck inside the future. So why do we need pin in the future truck?
Great question. I mean, I can answer it. Sure, we have time, so I'm going to answer it. So just to figure out where it's going to be. So I think it's this one. Yeah, so maybe this. So basically, if you remember our async tree or the tasks tree we had before, do you remember this model, or do you want me to go back to it?
Yeah.
You remember it. So basically, in this model, right, you remember I said it's like the stack of the task we spawn. And in this stack, we may have something that's called like a self-reference. So we may have references to data that lives inside this stack. And the problem with self-references is what's going to happen when we move the struct around. So in Rust, everything is movable by default. So tell me, what is going to happen when we move the struct around?
The variable will be wrong.
So the reference is going to be invalidated.
Yeah.
And what it means that we really don't want people to move our futures around. So this is what pin for. Pin is just a marker. And it's just a marker that is going to tell us that whenever we pin a struct, you can move the struct in memory anymore. And why pin is not a trait? Why is it actually a struct? Why is it a struct marker? So the reason pin is a struct marker is we still want to be able to move the future just before we actually call the poll function on it. I mean, otherwise, we also have this unpin trait. And anything that implements this unpin trait is actually something that doesn't have self-references inside it, so it doesn't suffer from the problem of moving it around. So we can freely just pin it, unpin it, and move it around in memory. And it means that something like box, which is just a pointer, is basically free to move in memory no matter what it points to. Because even if what we have inside the box has self-references, it doesn't implement unpin, the box itself is just a pointer, so it can freely move in memory. And this is why we just boxed our futures, and when we can just pin boxed futures because the moment we have box, everything is unpin, everything doesn't have self-references, and we can just move happily things around. Now, I think this is pretty much anything I have to say on pin without getting too much in details about what is marker, why do we need marker again. Like this has to be a lot weight unsafe, and yeah, it has to do a lot weight unsafe. This is like, and like if I can say another word about pin, so whenever you create pin, so you ask me, wait, who promises this us? This is just a marker. So if your struct implement unpin, it doesn't have self-reference, it can just pin itself, unpin itself, everything is safe. If your struct has self-references in it, like a future that captures some kind of value by reference inside it, it's not going to implement the unpin trait. And it means that if you want to pin it, and you don't use something like box, you want to directly pin it, you're going to need to use unsafe. So the function to create pin from something that doesn't implement unpin is unsafe. So it's on you to verify this invariant and tell anyone that uses your pin struct that isn't supposed to move around, that you promise it's not going to move around anymore.
I would mention like there's a phantom pin.
So phantom pin is like when you want to create a future by end and you want to tell people, hey, this function. So to go a step back, basically our struct, any struct in the system like the unpin trait is like an auto trait. So any struct just implement unpin by default, unless it has like an unpin thing inside it. It works the same way like send or other auto traits you have probably seen before. And when we create a future by end, and I really don't want you to do it, but if you decide to do it and you create a future by end, you are going to need to tell the system, hey, don't implement unpin for me. I'm not safe to move around. And to do it, we usually use phantom for this thing. With pin, we need to use something that's called phantom pinned, I guess. Anything else? I think we are done, so.
All right, thank you for the talk.
I still have some works.
Stay on for a second.
I still have works.
You still have notes?
Yeah, I still want to thank everybody. So I first of all want to thank Mate for organizing this amazing event and allowing me to present here in front of all of you and actually guiding me through this process. So if anyone wants to present in the future, you're getting to work with this guy, and it's an amazing guy. It teaches me a lot of good things. I also want to thank Shores, and I don't really see him on the crowd. Shores also give me really good, I guess, points to. He's seen the dry run of this presentation and give me some good advices, high quality feedback to make it really be the way it is right now. And I also want to thank Remy Clerc for inviting me for a drink and really bringing up the idea of this talk. And thanks for him, I'm even standing here right now. And he was really good friend through the process, answering whatever stupid questions I have on Discord. And I also want to thank everybody for listening to me, giving me your time. Thank you.
Thank you for the talk. And as you can see, if you want to present, don't be shy. You have a community to support you, to help you prepare the presentation. All right, I'm just going to do my usual questions. So how did you get into doing programming?
How did I get into programming?
Yeah.
That's a long time ago. So, I was a bored children. I played video games, and I wanted to create servers to play with my friends. So I kind of got into programming passively, I guess. That's it.
How old were you at the time?
I was about 12 years old, I guess.
Pretty cool. What was your first programming language?
I don't like this question. So my first programming language was Sourcepawn. I don't think anyone really knows it here. Sourcepawn is part of something called source mode, which is a kind of runtime for something called the Source SDK, which is the engine Valve uses for its games. And this is just a scripting language that looks like C, compiles into bytecode and runs on source mode.
That makes sense. So you're just really serious about making games?
Not games. It was creating the servers inside the game so you can play with your friends.
What's the first quote unquote, programming language that you use that you're still using
So
occasionally?
that I still using.
That you're still using?
Oh, I mean, Rust is the only language I use nowadays, I guess. I mean, but the first three language I used, I guess, is either PHP or JavaScript. I wanted to like create a web server that can interact with my server that uses source-bound, so I've started to learn web programming.
What's the language you used before Rust?
So before Rust, I like avidly used C++, so it was like a fun move.
So what was the most difficult thing for you to learn when you
When I've
started
learned
on
Rust, what was the most difficult thing to
coming
learn?
from C++?
I don't know. Yeah, I don't have a good answer for you, sorry.
All right. And I guess last but not least, what's a topic that you would like to see here somebody present about?
What a topic I want somebody to talk about. So I think any topic is welcome. And I personally really like security, like it's like an hobby on the side. So if you have security things to talk about related to Rust, like somebody reads assembly for daily life, I don't know, and wants to tell us some things about reversing Rust binaries or something, I would be happy to hear about it. Anything else?
Nope.
So
I'm
we're
out of
done.
questions. Well done. Thank you for the presentation.